Okay, same FRQ, part C now. Find the absolute minimum of G on the interval. Justify your answer. Min-max theorem problem. So in this case, I'm not working with F, I'm working with G. So let's see, absolute minimum. So the minimum of G is either at the beginning of G, end of G, or a relative, this case would be minimum of G, or where G prime is 0. There's a shortcut here though, because we've already, again, they're trying to get you to see how the different parts of the FRQ connect. So, they've already told you, like we've already had to think about this. This is G prime. We can see that G prime has negative y values. Then at x equal 1, 2, 3, 4, negative, G prime switches to positive y values. So we need to make a note of that. G prime, because we have to justify our answer, changes negative to positive at x equal negative 4. So G has relative min at x equal 4. At. The min-max theorem says that's going to be, negative 4. That's going to be where G is lowest, or it could be the end points. I have to do something to justify it. Absolute minimum. I think I like words in this case, because I can go find the values of G, and that's what we did before when we had a calculator available to us. Now that we don't have it, that's what we did on like test 4. But now that we don't have a calculator available to us, I think it's easier to say the following. For x equal negative 5, including that negative 5, all the way to x equal negative 4, G prime is negative, so G is decreasing. That means the graph of G is going down for these x coordinates. G is going down. Then, the trouble is G goes back down over here, so I'm still going to have to find that. This is the point where I might move on to a new FRQ because I can start to feel myself getting stuck. But I have found this, so I have earned 1 point so far. We'll keep going so you can see how to solve it. It does look like I'm going to have to do some integrals. So let's just go ahead and do them. So I'm going to copy this over. And we've already done the pink, so now what we do is we say G has absolute min at x equal the beginning x coordinate, or the x coordinate where G had a relative min, or the x coordinate at the other end. And now we need to find each of those. So we have a formula right here. So G of negative 5 is going to equal the integral from negative 3 to negative 5. That catches my attention because I'm always going slow and careful. This is backwards, so we're going to fix that in a second. Oops, that's a T. So we do -1 multiplied by, reverse the limits. So we're starting at -5, going over here to -3. Here the values of f are all negative, so whatever the area is here, that gets counted negatively. Here the values of f are positive, so that area gets counted positively, but those two areas are the same. So this integral's value is going to be 0. So g of -5 is 0. We need to go find g of these two values. So I just keep doing the integrals. So we're going to copy that over, get some more space. So I need to do g of -4. Still using this formula. Switch the limits so I don't go backwards. So we're going from -4 to -3. So we're finding this area. All the values of f here are positive. So this will be positive. So that's, let's see, that's 2 high and 1 wide. Half of that is 1. So this integral's value is 1. But I had a -1 multiplier. Oops. Had a -1 multiplier. So I just found out that g of -4 has a value of -1. I still have to go check one more point. Got to go find what g of 4 is, because those are the places where g could have been lowest. So copy this. I'm finding g of 4 now. The integral from -3 to 4. That one does not need to be reversed. So from -3 all the way to 4. So along here, the values of f are all positive. So all of this area in red will count positively towards the value of the integral. But the area down here in green, where f has a value that is negative, that counts negatively. So just break it up. So again, breaking this up, 3 times 1 is 3. So g of 4 is going to equal 3 plus 3 halves plus, I need to find the area here. So there's a rectangle that's 2 wide and 1 high. So plus, the rectangle's area is 2. You take away from that rectangular area the area of this semicircle. That's pi over 8 multiplied by the diameter squared. Diameter here is 2. So that's going to be the area in red, right here. Still need that little area. Plus 1 times 1, half of that's a half. Plus, that's the opposite, -1/2. So those two add to make 0. This will obviously be a positive number because all of this area is positive. knowing that that's positive is good enough, because the whole goal of the problem was to figure out where's the absolute min of g on this interval and to justify our answer. So we have now in our work, we've shown that there's only the only place g could have an absolute min is x equal -5, x equal -4, or x equal +4. We know that at g equal -5, the y-coordinate is 0. At x equal -4, the y-coordinate of g is -1. And at x equal 4, the y-coordinate is some positive number. That work is now sufficient. So you can say, therefore, g of x has an absolute minimum value of -1. Because I found the answer, I get the second point. Because I had the proper justification, I get the third point. So key things again. The first point was for properly identifying right here in pink. So this was this point. Then I remembered the min-max theorem, so I knew I had to go check these 3 x coordinates. So I did 3 integrals. 1, 2, 3. By doing that, I figured out that g of -4 is equal to -1. That gave me this point. And that allowed me with the other integrals to have the proper justification for the final third point. The 3 integrals are the justification.